In this video we're going to practice using synthetic division in order to find polynomial quotients or division with polynomials. But the reason why we can use synthetic in the first place is because of what we call the remainder theorem here. So this remainder theorem, let's go ahead and recap what it says. It says if you were to take any polynomial function, and we'll call it f of x, if you were to take that and divide it by x minus k here, some factor x minus k, then what's going to happen is this. We say the remainder is always going to be r equals f of k. Okay. So here's the thing I want to kind of make abundantly clear. We're saying we're taking some f of x here, and we're dividing out some x minus k, and we're getting some quotient here, but the remainder is equal to f of k. What this basically means is if we were to rewrite this thusly, we say we have some f of x that's all populating this right here up to some certain point. I don't want to say it approaches 1, but with f of x, it goes out to here somewhere, and we're dividing by x minus k. Then what I'm going to say is that this remainder over here is actually equal to f of k. So the weird thing is this. If we were to do this synthetically, which is what we want to do here, then we would get the same results. And so we're going to build on that result at the end of this video. Let's go ahead and just work on how you find quotients synthetically. So synthetic division with and without a remainder. We say what I want to do is I want to take this polynomial f of x here, and I want to divide it both by this factor here, x to the first minus 2, and also by x to the first plus 3. So first things first, let's point out one very important thing. It says it can be used to divide polynomial, and that is synthetic substitution. It can be used to divide a polynomial by an expression of the form x minus k. So we can, well, let's put it this way, only use synthetic division, so synthetic division, if and only if dividing by first degree divisors. Okay, so when I say first degree divisors, I mean divisors of the form x to the first minus some constant k. Okay, so you can see that clearly both of these right here are those things, and so we say, well, let's go ahead and divide these synthetically. So in both cases, what we do is we drop the dividend inside of this array here. We drop its coefficients. So we say 1x cubed, 2x squared, negative 6x to the first, and negative 9 constants. And so now, this is really interesting. We're going to divide by x minus 2. So now the interesting thing here is this. We say it's a factor of the form x minus k. Now if I were to write x minus 2 and say, well then what does k equal? I get a lot of people here that tell me that k equals negative 2 because that's the number right here. Where indeed we could rewrite this really as x minus some value k. And what I can tell you is if k, which is this number right here, is truly equal to negative 2, then what you would really get is this statement, x minus a negative 2, which is x plus a 2, and this is true when k equals negative 2, you produce this thing right here. So since we're dividing by x minus 2, the thing we need to draw apart from it is this. This k value here is the opposite of what this is in the factor. So when we say, what should I put out here? Remember, we put out actual x values over here, and we say, let's go find now when we divide by x minus 2 what we get. That means that x actually equals a positive 2 here. Okay, so what we're going to do is we say it's the opposite of this number right here, this k number. So we'd say carry down the leading coefficient, we get 1. We say 2 times 1 is 2, plus 2 is 4, times 2 is 8. 8 plus a negative 6 is a positive 2, 2 times 2 is 4, and then we say 4 plus a negative 9. So the things basically we're going to mark down right off the bat are these. This first of all is f of 2. It's also the remainder. It is the remainder. Okay. So since that's a remainder, here's how this works. If that's the remainder, r, then we're going to go put our variables back into this quotient, which this is the quotient. So we say 2 is our constant term, 4 is our x to the first term, and 1 is our x squared term. So what we really get here is this, the quotient. The quotient. And the quotient comes out to be this, 1x squared plus 4x to the first plus 2 plus negative 5 over the thing we were dividing by, which was x minus 2, which I got from right here. So this gave us a remainder here. I'm going to go ahead and draw on this last example where we're going to use the same polynomial. We say 1, 2, negative 6, negative 9. And this time we're going to divide by x plus 3. So if x plus 3, this is like our x minus k here, x plus 3, I'd say then what is k? K is actually negative 3 from this here. So we're going to say we'll plug in a negative 3 out here, the opposite of what we have in our factor right here. and we'll carry this out again. So we say negative 3 times positive 1 is negative 3. 2 plus a negative 3 is a negative 1, times a negative 3 is a positive 3. Negative 6 plus a positive 3 is a negative 3, times a negative 3 is a 9, and then 9 plus negative 9 is 0. So a few things I want to say here. First of all, the remainder, let's mark this down. Remainder is 0. Actually, I'm just going to write 0. I don't want to write an exclamation point after it because that means something else. So I'd say remainder is 0. Also this, we would say that our quotient this time is, let's see, our constant, x to the first, x to the second. You just count backwards here. We say is x squared plus, sorry, let's do this, minus 1x. So minus x minus 3. So the last thing I really want to kind of admit to ourselves here is this. When you do a division problem like 8 divided by 4, say, is 2, or in this case it would be more appropriate to say 8 divided by 4 is 2, what I want you to see is this. The quotient, if you were to take the answer you got times the thing you divided by, then what you get back is the dividend you started with. So the fact that this came out to be a 0 means a couple of things to me. First of all, no remainder means that x plus 3 is a factor. Means it went in evenly when I divided it out. Furthermore, the thing I divided out, x plus 3, if I were to take it times the answer I got, which is x squared minus x minus 3, I would get back the thing I started with. So this is a very nifty tool in the fact that what we did was we started with some third-degree polynomial. And what I said is, because of the fact that we obtained a remainder of 0, it means that we can rewrite the original expression as the answer I got times the thing I divided out gets me back to what I started with. So two things that can be said here. When the remainder is equal to 0, then the thing you were dividing out is a factor. Okay? And also this, if this is a factor, then we can rewrite the original expression in a factored form. And recall that a factored form expression is very desirable, especially when you set this equal to 0, because then you could say, well, then either this was 0 or this was 0. Cheers.